Hi everyone, this is Jinhao from Shanghai Tech University, China. Our laboratory is PSPAL, which is Power System Protection and Automation Laboratory. The title of my paper is General Fault of Phase Mode Transformation Matrices for Three-Phase Power Systems and Applications to Transmission Line Protection. Firstly, I will introduce the background of my paper. The phase mode transformation matrices are widely used to decouple the three-phase AC systems into independent modes. Under the description of modes, we no longer need to care about the influence of mutual inductance, which simplifies the system analysis. Up to now, there are many common decoupling matrices, and their detailed forms are shown in this table. The symmetrical component transformation, also known as 1-to-0 transformation, is adopted in phasor domain analysis because the elements contain complex numbers. The Park transformation is applied in electrical machinery to convert time-varying pure sinusoidal waveforms into constant values. The Clark transformation is used on protection and fault locations. Other matrices like Wedpol and Columbia transformation also have its own application theme. This paper focuses on the decoupling of symmetrical three-phase system. Thus, the currents and voltages in 1-to-0 forms can be expressed by the decoupling matrix T inverse times the currents and voltages in ABC forms. At the fault location, the fault phasor currents are related with the fault phasor voltage through the fault admittance matrix YABCF. Combining the two equations, and we get Y1-to-0F, which connects I1-to-0 and V1-to-0. To promise the complete decoupling, the basic conditions are shown in advance. Furthermore, we put emphasis on additional objectives. They bring more restrictions on the elements of matrices as well as provide better properties. For instance, if objective A holds, the specific mode can be utilized in protection and fault location applications, regardless of fault type. If objective B holds, the voltage and currents of this specific mode can be calculated without requiring any other modes, and can greatly simplify the fault analysis procedure. The objective C further assumes that only one element is non-zero on the basis of objective B, so the analysis of one term includes all the information of the specific fault. There are the detailed requirements for each objective besides basic conditions. Notice that objective B, C, and D aim at the specific fault, so each fault type needs discussion respectively. The results directly follow the definitions of objectives given before. Take the objective A as an example. The definition is that the component of one specific mode always exists for all types of faults. It numerically means that at least one of the three elements of a fixed row is non-zero, so the final conditions are a series of equations. What's more, one can observe that the first mode and the second mode are dual. Once the conditions for the first row are derived, the conclusions for the second row can be drawn right away. For instance, for the first row to hold objective A, it requires P11 is not zero. So P21 should be not zero for the second row to hold A. After the derivation of additional objectives, the paper then analyzes existing widely adopted transformation matrices. It is obvious that they do not satisfy objective A. Under this circumstance, this paper proposed an example matrix to fit objective A. From the simulation results, one can observe that the mode 1 differential current is pure zero for common matrix during some faults. To be specific, multiple transformation fails to detect phase B to ground fault. Column-Bayer transformation fails to detect phase C to ground fault, and Clark transformation fails to detect phase P to phase C fault. However, the proposed matrix, which corresponds to the purple line, correctly works during any faults. Here are some conclusions and recommendations for this paper. This paper comprehensively presents the general fault of phase mode transformation matrices for three-phase symmetrical power systems. Specifically, the paper derives not only the basic conditions to ensure complete decoupling, but also the extra conditions to meet additional objectives to simplify the design of protection and fault location. After that, a matrix which enables correct operation during all fault types using one fixed mode is proposed and approved. Finally, for various applications seen, the objectives discussed in this paper can act as a guidance on selecting transformation matrices for various applications, such as protection and fault location.